Good morning, everybody. Welcome to the lecture on the biomechanics of the spine. In this lecture, we will be discussing about the structure, function, movements and loading of the spine with special emphasis on the lumbar spine, followed by calculations of static loads and bending moments in the lumbar spine using some solved problems. The vertebral column, also known as the backbone or the spine, is a part of the axial skeleton. The human spine consists of 33 vertebrae, each vertebra stacked over the other. It consists of the cervical, thoracic, lumbar vertebra. These are the main three regions, followed by the sacrum vertebra and the coccyx. The cervical vertebra has 7 vertebra, C1 to C7. There are 12 vertebrae in the thoracic segment and 5 vertebrae L1 to L5 in the lumbar segment. The sacrum consists of 5 fused bones in the pelvic region, followed by the coccyx, where there are 3 to 4 fused coccygeal segments. The vertebral the spine can be considered as a modified elastic rod because of the flexibility of the spinal column, the shock absorbing capacity of the disc and the stabilizing function of the ligaments. A healthy spine has 3 natural curves that resemble a S shape in the sagittal plane. These curves absorb shocks on the body and protect the spine from injury. Let us discuss about the relationship between the structure and function of the spine. The structure of the spine withstand the combined load of the head, shoulder and thorax. The upper body weight is transferred to the lower extremity through the sacrum and the pelvis. So, the resistance to the axial loads on the spine are offered by the S curve in the sagittal plane. It is a S-shaped curved structure. And also due to the increase in size, mass and load carrying capacity of each vertebra as we move from C1 to the sacrum. The elasticity of the spine is accomplished by the curved shape of the structure, as already indicated earlier, and the multiple motion segments or the functional spinal units. We would be focusing further discussions mostly on the lumbar spine segment, because the lumbar region actually carries the bulk of the upper part of the body weight. Now, let us come to the lumbar spine now. As you can see, it is located in the lower part of the vertebral column, and the main function of the lumbar spine is to bear the weight of the upper part of the body and transfer the forces and bending moments to the sacrum. The vertebra in this part of the structure or the segment are much larger in size to withstand heavy loads during daily activities. The lumbar spine is more mobile than the thoracic spine and also carries more weight, making it the most likely region susceptible to injury in the whole spinal structure. The range of motion offered by the lumbar spine are combined flexion and extension. So, the range is given from 40 to 90 degrees, the lateral bending 20 to 45 degree, and rotations between 5 to 15 degrees. Typically, the structure of a lumbar functional spinal unit is shown here, and a lumbar vertebra is also shown here. Let us discuss about the movements of the spine. Flexion and extension in the sagittal plane, as indicated here in the figure, bending forward, bending backwards in the sagittal plane. Lateral bending left and right in the coronal plane. And rotation left and right in the measured in the transverse plane. We would now focus on the spinal muscles. The functions of the spinal muscles are to provide stability to the trunk at any posture and to produce movements during physiologic activity. The muscles can be broadly classified as flexors and extensors. The muscles anterior to the vertebral column acts as flexors and posterior to the vertebral column acts as extensors. The extensors muscles are erector spinae, multifidus and intertransversary. The flexor muscles are abdominal and psoas. Let us discuss about the loads acting on the spine. On the left, we can see a multiple bar diagram which presents normalized spinal loads in various body positions calculated with respect to the load during upright standing, as indicated in the figure. The loads are minimal during well supported reclining, remain low during relaxed upright standing, as you can see here, and increases during sitting without support. The highest load on the spine, the highest loads on the spine are generally produced by external loads such as lifting a heavy object. The factors influencing the spinal loads are the size, weight and position of the object to be lifted with respect to the center of motion of the spine. And the second important point is the posture, position of the center of gravity of the upper part of the body with respect to the center of motion of the spine. Now, the loads on the spine is dependent on the body position. The body position affects the magnitude of the load acting on the spine. In a supine position, loads on the spine are minimal because the body weight is eliminated. Forward bending produces a bending moment on the lumbar spine calculated as a product of the upper body weight and the lever arm. The lever arm is indicated as LU and the weight of the upper part of the body as U. Forward bending generates increased tensile and compressive stresses due to bending in the vertebral functional unit. The forward bending generates increased tensile and compressive stresses in the disc due to the bending action. Now, let us move towards the second part of the topic, that is based on calculation of bending moment on the lumbar spine. The first problem. These problems are rather simple problems, but it presents the idea of the effect of the load position and the posture, how these two factors affect the forces and bending moment on the lumbar spine. Now, man is carrying a weight of 100 Newton, carrying an object of weight 100 Newton in a standing position. Now, the distance from the center of motion of the disc to the center of mass of the object এটাকে মুছতে হবে। The distance from the center of the distance from the center of motion of the disc, which is indicated by here, to the center of mass of the object can be calculated as 25 centimeter as indicated in the figure. The center of motion of the disc in a functional spinal unit is indicated here. Now, the bending moment acting on the lumbar disc is equal to the load of the object and the lever arm, which is given here by L, the distance L. So, if you multiply the load of 100 newtons by the lever arm of 0.25 meters, then we actually can calculate the bending moment on the lumbar spine. The second problem presents the influence of the lifting technique on the loads of the lumbar spine. So, a person is lifting an object of same weight 100 newtons using three different techniques. So, one is the forward bending, which is indicated in the figure A, with knees bent, but more in an erect position. So, the weight is carried closer to the body in the case B, and the third case C is forward bending with knees bent. So, you can see here that there is forward bending and the weight is being carried in a position when the knees are bent. So, the LU, the lever arm of the weight of the upper part of the body, and the length of the lever arm LO of the weight of the object are different for 3 different cases. So, we will take up now each case and calculate the bending moment. So, the first case is calculation of the bending moment during forward bending. So, during lifting with forward bending, as indicated here in this figure, the lever arm can be taken as 40 centimeter. So, assuming lever arm as 40 centimeters, we can calculate bending moment acting on the lumbar disc produced by the object is equal to 100 Newton multiplied by the lever arm, and that is 40 Newton meter. Assuming LU or the lever arm of the upper part of the body as 25 centimeter, the bending moment on the lumbar spine produced by the upper part of the body is 300 Newton multiplied by 0.25 meters, which gives a bending moment of 75 Newton meter. So, the total forward bending moment is sum of these two bending moments, 40 Newton meter plus 75 Newton meter, and that gives 115 Newton meter. Now, for the second case with knees bent and back straight, so it is much more in an erect position, but the knees are bent. The object is positioned closer to the trunk. This is a very important position, thereby decreasing the forward bending moment. This can be proved by the following calculations. So, assuming the lever arm of the object as 35 centimeters, the bending moment on the lumbar disc produced by the object is 100 Newton multiplied by 0.35 meters, which gives me 35 Newton meter as the bending moment. Assuming the lever arm of the upper part of the body as 20 centimeter, the bending moment on the lumbar disc produced by the upper part of the body is 300 Newton multiplied by 0.20 meters, that is 60 Newton meter. So, the total forward bending moment is calculated as 95 Newton meter, which is sum of the bending moment produced by the object and the bending moment produced by the upper part of the body. Now, this value is less than the value calculated in the first case, case A. In the third case, we are calculating the bending moment during forward bending with knees bent. So, during lifting with forward bending and knees bent, the object is held far from the trunk. As you can see in the figure, thereby increasing the forward bending moment. So, assuming the lever arm of the object as 50 centimeter, the bending moment can be calculated as 100 Newton multiplied by 0.50 meters, that is 50 Newton meters. This is the bending moment produced by the object on the lumbar disc. Assuming lever arm as 25 centimeter of the upper body weight, the bending moment produced by the upper body weight is 300 multiplied by 0.25 meters, gives a bending moment of 75 Newton meter. So, when we add these two bending moments, 50 Newton meter and 75 Newton meter, the total forward bending moment is calculated as 125 Newton meter, which is the highest of among all the three cases. Now, let us now discuss on the static loads. We will perform some calculations of the static loads on the lumbar spine, and this is the third problem that we are undertaking. The loads on the lumbar disc is calculated at a point for a person weighing 60 kg and lifting an object of weight 100 newtons. So, the 100 newton is the weight of the object, and we assume that the spine is flexed at 35 degrees approximately. Now, in this case, we identify three main forces that are acting on the lumbar disc, as you can see here also in the free body diagram. The forces produced by the upper part of the body weight, that is 300 Newton, assuming approximately 50% of the body weight, total body weight. The forces, let us now discuss about the three main forces acting on the lumbar disc. The first one is the force produced by the upper body weight of 300 Newton, which is approximately half of the body weight. The second point is the force produced by the weight of the object, that is 100 Newton. And the third is the force produced by the contraction of the erector spiny muscle, indicated by the force Fe here in the free body diagram, with its direction known, but the magnitude of this force is unknown. So, we try to zoom in this lumbar segment and try to get a more detailed picture of the forces acting on the lumbar spine in this position. So, we have the axial forces acting on the lumbar disc, the tangential forces or the shear forces that is also acting on the lumbar disc. You can see here the erector spiny muscle force Fe acting at a lever arm Le, and this unit or the lumbar disc is oriented at 35 degrees to the vertical axis as well as the horizontal axis. Let us continue with the calculations of the static loads on the lumbar spine, and let us identify the lever arms. So, the lever arm of the object O is 40 centimeter, lever arm of the upper body weight U is 25 centimeter, and lever arm of the muscle is 5 centimeter. Now, for the body to be in moment equilibrium, the sum of the moments acting on the lumbar spine must be equal to 0. So, we add all the moments about the center of motion of the lumbar spine and equate it to 0. So, when we do that, we generate an equation from which we can calculate the unknown force or unknown magnitude of the force applied by the muscle erector spinae, which is equal to 2300 Newton. Let us focus our attention on the calculation of static loads on the lumbar spine. So, we will be calculating the axial force F and the shear force T as indicated in the figure, which are acting on the disc, which is inclined at 35 degrees to the transverse plane. So, the forces that are acting in this problem are the compressive force of the weight of the upper part of the body, which is taken as 300 Newton. So, the component that is acting along the y direction is u cos 35. The force of the weight of the object O as indicated in the figure. So, if we take the component along the y direction, it is O cos 35, and the third force is the muscle force of erector spinae muscle, which is indicated as Fe, and this is oriented along the y direction as indicated in the figure. Now, if we resolve the forces along x and y directions and considering equilibrium, we can generate two equations, one along the y direction, one along the x direction, which are stated here in the slide. From each of these equations, we can actually find out the value of the axial compressive force F. Now, in this equation, we can substitute the value of Fe, which we had calculated earlier in the earlier slide. And in the second equation, from the second equation, we can find out the value of the shear force T. So, finally, we arrive at the solution that the compressive force F is 2627.6 Newton and the shear force T is 229.4 Newton. Let us come to the conclusions of this lecture on the spine. The curvature of the spine allows the vertebral column to withstand high loads. The muscles provide stability to the trunk at a given posture and enable movement during physiological activity. Body position affects the magnitude of the loads on the spine, and the factors influencing the spinal loads are the position and weight of the object carried and the posture of the body. The list of references is presented here, based on which we have prepared the lecture. Thank you for listening.